Hi teacher, my name is Vương Anh Nhật, and today I want to present a scientific paper called a 3D Civil FPGA DRAM hybrid architecture for low power computation. First of all, I want to say because this is the very long scientific paper, so my slides are only image. I will talk about the abstract part. The power bucket is a way to limit the portion of the chip that we can power on at the upcoming technology nodes. This problem known as the utilization war of dark silicon is becoming increasingly serious. With the introduction of 3D interactive circuits, it is likely to become more serious. So how to take the advantage of the extra transistor made available by Moore's law and the one set of the 3D ICs within the power bucket pose a significant challenge to system designer. Let's talk a little bit about Moore's law. Moore's law is the observation that the number of transistors is the iterative circuits doubles about every 2 years. Moore's law, rather than a law of physics, it is an empirical relationship linked to gain from experience in production. To address this challenge, they propose a 3D hybrid architecture consisting of a single layer with multiple cores, a few programmable gate array FPGA layer and DRAM layer, and this 3D hybrid architecture help the system translate to 47.5% power reduction relative to a baseline system that consists of a CPU layer and DRAM layer. This is also translated to a 72.9 power reduction relative to an alternative system that consists of a CPU layer, an electric cache layer, and a DRAM layer. Then next we will move to the instruction. The power consumption is among of the top concerns today of today's chip designer. On downwards now continue to enable increased transistor count. The power bucket constrains the power portion of the chip that we can power on. This problem, known as the utilization war of dark silicon in the 3D ICs, multiple dies are stacked together in one packet, making more transistors available than predicted by Moore's law. This means designers have more transistors than they can afford to power on. Thus, they face the challenge of how the extra transistor can be translated to better performance under the given power bucket. Adding specialized accelerator to add general-purpose CPUs has been proven to be an effective method for reducing power computation. This accelerator includes coprocessor with special instructions, general-purpose graphic processing units (CPUs), field programmable gate arrays (FPGA), and application scientific ICs (ASIC). Of the three options mentioned above, FPGAs provide a higher flexibility and residual power efficiency, making them perfect candidates for low power computation. Previous studies have shown the advantage of FPGA over CPU and GPU in this respect. For example, Kester showed that using the FPGAs for basic linear algebra subroutines can achieve 2.7 to 20 293 better energy efficiencies than using GPUs and CPUs. They propose In this paper, they propose a 3D hybrid architecture for low power computation to forestall the dark silicon problem while enabling the highest performance possible without hitting the power wall. The architecture is easy to use and meant for general purpose computation. It consists of CPU layer and the FPGA layer and DRAM layers. It takes advantage of through silicon via TVS based 3D IC technology to provide vast FPGA resources close to CPUs. Their experimental methods results so that compared with the our CPU, The accelerators on the FPGA layers can reduce function level power and EDP by 6.9 and 7.2, respectively, and application level power and EDP by 1.9 and 2.2, respectively, while delivering similar performance compared with a baseline system consisting of CPU layer and a DRAM layer. They both architecture can achieve 47.5% power reduction for the entire system, compared with the alternative system consisting of a CPU layer, an L3 cache layer, and a DRAM layer. And the entire system can achieve 72.9% power reduction. The summary of this paper as follows. One is they propose a new 3D architecture with the CPU, FPGA, and DRAM layers for low power computation. Two is they demonstrate a communication mechanism that allows the FPGA layer to access CPU data cache. Three is they develop a new framework to evaluate the proposed architecture. Four, they evaluate performance, power, and thermal impacts of the architecture, both at a function and application level. We will move to the related work. They show that their proposed architecture can overcome this drawback using 3D stacking. This not only enables fast communication but also provides enough FPGA resources and takes advantage of the state-of-the-art FPGA design. Designing FPGA-based accelerators requires hardware expertise, which is a parallel to wider adoption of reconfigurable computing systems. Fortunately, recent development in XLS have significantly lowered this barrier. XLS tools directly to convert the function written in high-level language to hardware accelerators. Some researchers have also studied the direct computation of Compute Unified Device Architecture CUDA or OpenCL, designed for heterogeneous parallel computing to hardware. The 3D IC has multiple layer dies, which are connected by the TVS stuck in a single packet. This method collect more than can more possible. And this is the image. This is the image. Description the layer they propose. They propose a hybrid CAD 3D architecture consists of 3 layers. One is CPU, 2 is FPGA, and 3 are DRAM layers. An extended configuration may consist of multiple FPGA and DRAM layers. The cores located on the CPU layers run at a high frequency, 1 GHz or higher, and generate the most heat. Therefore, the CPU layer is located closer to the heatsink. This is the heatsink. To explain the heat distribution adjacent to the CPU layers is the FPGA layer. The FPGA layers, it contains an accelerator for low power computation. This accelerator runs at a much lower frequency, several hundred MHz, than the CPU cores. As a result, they generate much less heat and are placed farther from the heatsink. Above the FPGA layer is the DRAM layer. It contains a system memory. It usually generates the least heat and is hence placed farthest from the heatsink. Such a design has several advantages. Accelerator can use the existing infrastructure, including the CPU memory hierarchy and memory controllers, which saves hardware resources. 2. Cache on the CPU layer can exploit memory access and increase accelerator performance. 3. Sharing cache provides a uniform view of memory space among the CPU cores and accelerator. 4. Sharing cache eliminates the need for copying data, enabling fast switch between the CPU core and an accelerator. This feature so that the original function in C, which multiplies a matrix A and B, and store the result as a matrix C. All the matrices are stored in a round major order in the function. The two outer loops iterate through each element of matrix C, and the innermost loop iterates through the corresponding row of matrix A and column of matrix C B to calculate the matrix C element. This is the code, and this figure so that the generate accelerator structure input A and B and C are pointed and mapped to three memory access interface. Input argument N is mapped directly to value passing signal. In the generate accelerator, the database contains four multipliers to multiply four pairs of inputs and three adders to sum up the products. And the table 1 uses instruction to directly to conflict a called accelerator also allows a fast switch between the CPU and accelerator. A typical call to an accelerator has two steps. One is the CPU use the write instruction to write accelerator register, and two is use the run ACC instruction to start the accelerator and receive the execution result. During the instruction execution, an accelerator may access memory through the CPU data cache. Meanwhile, the CPU waits until the accelerator finishes all translation. Look aside buffer TLB miss occurs. And an FPGA accelerator can access the CPU data cache directly. To enable this sharing, a switch is added to enable multiplexing as shown in figure that at any given time, either the CPU core to accelerator has access to the data cache. Since the switch only has a 2-to-1 multiplexer between the CPU kernel and the data TLB cache, it only incurs a minor increase in path delay, which we analyze further in section 5. The CPU and accelerator are connected through a pair of FIFOs. These FIFOs are used as buffers to alleviate the mismatch because the CPU core operates at a higher frequency and the accelerator at a lower one. These 6 types of packets are used for CPU accelerator communication. We will do accelerator communication. As so in this figure, one is starting an accelerator. The index field of the packet indicates the index of the accelerator. 2 is right. Writing an accelerator register. The index and value fields of the packet indicate the register index and value to be written respectively. 3 is memory response. Return memory to read result. The value field in the packet is memory read result. 3 is done. 4 is done, indicating accelerator execution is finished. The value and size fields in the packet indicate the value and data size of return values. If it exists, respectively, binary code 0001, 10, and 11 indicate 1, 2, 4, and 8 by data size respectively. 5 is memory read. Reading memory, the address and size fields correspond to the address and data size of the read operation respectively. Data size encoding is the same as above. And the last is memory write. Writing memory, the address, value, and size fields of the packet correspond to the address, value, and the data size respectively. Data size encoding is the same as above. And this figure shows an example of an accelerator with duplicate channels for pointer argument A. And as mentioned earlier, the CPU data cache has enough bandwidth to fit the duplicate channels. If this bandwidth is still not sufficient, we can create multiple swap batch memories inside the FPGA. And the next part is evaluation framework. We will move to this evaluation framework. And they design the customized framework to evaluate their robots architecture, and this figure shows the structure of the framework. It consists of 4 parts. One is HLS, that means high-level synthesis. 2 is performance simulation. 3 is power simulation, and the last one is thermal simulation. The HLS part contains the Vivado HLS, which converts a C++ function into accelerator hardware at the register transfer level. The function to be converted is chosen based on software profiling result. The generate accelerator has multiple versions with the same underlying hardware structure but is written in different languages. Verilog hardware description language which HDL and System C. Then a script has the accelerator interface and change the benchmark score to use the generate accelerator instead of the original function. The new score is not compiled into an executable binary for performance simulation. And this table is system configuration for the VHDL framework. The last one, and the important part in this paper is experimental result. They compare the power, energy, performance. First, we will compare CPU versus accelerator, function level, power, energy, performance, and ADP. They compare the power, energy, performance, and ADP out of the other CPU core and the FPGA accelerator when running the same function. The first two parts marked as CPU and ACC. The CPU and ACC. And on the figure, compare the power, energy, execution time, and ADP of the CPU is CPU only, and the FPGA accelerator is CPU plus ACC. All the results are normalized to that of the CPU. When estimating the CPU power and energy, we include the data cache (TLB) and instruction cache (TLB) inside the core. When estimating the accelerator power and energy, we only include the data cache and the TLB, since accelerator only access them. In the second figure, description the benefit of accessing data directly from the CPU data cache. They measure the data cache bit rate of the CPU and accelerator result. The result is shown in figure and compare the amount of data cache accessed by the CPU and accelerator. On an average, the amount of data cache accessed by accelerator is only 23.6% of that of CPU. In summary, on accelerator bit rate lower than 9% and average is 3.6%. This means that the CPU data cache provides a very good caching for accelerators. Next part we move to the CPU virus accelerator, but we will compare on application level power, energy, and performance and EDP. From this figure, they found that CPU plus L3 performs very similarly to CPU only. The average execution time of CPU plus L3 is 99.8% of the CPU only. This is because the L2 case of the CPU plus L3 is big enough to accommodate the working dataset, rendering little advantage from adding an L3 cage. It confirms the fact that adding cage has diminishing returns after cage size exceeds certain thresholds. As a result, the comparison result between CPU plus L3 and CPU plus ACC are very similar to those between CPU only and CPU plus ACC. On an average, the power, energy, execution time, and ATP of CPU plus ACC with plus ratio L is 52.2%, 46.3%, 94%, and 46.3% of CPU plus L3 respectively. In this figure show the comparison of system power of CPU only, CPU plus L3 and CPU plus ACC. We found that CPU plus ACC consume much less power than CPU only. On average, CPU plus ACC reduce power consumption by 47.5% related to CPU only. By contrast, CPU plus L3 consume much higher power than CPU only and CPU plus ACC. This is because the L3 case of CPU plus L3 consumes considerable amount of power, even though we chose to use low standby power transistor for memory cells in the L3 case. On an average, CPU plus ACC reduced power consumption by 72.9% related to CPU plus L3. This figure shows comparison of maximum temperatures. We can see that maximum temperature of CPU plus ACC is much lower than those of both CPU only and CPU plus L3. On an average, the maximum temperature of CPU plus ACC is 49.7 temperature C and 6.4 degrees lower than that of CPU only and 9.5 degrees lower than that of CPU plus L3. This indicates that CPU plus ACC does not aggravate the thermal problem, which is a major problem in the 3D ICs. On the contrary, it helps to alleviate the thermal problem. And the last part is the solution. The FPGA layer implements the accelerator that works with several cores to achieve the low power computation. They also take advantage of HLS to make the proper architecture easy to use and suitable for general purpose computation. And in practice, experimental results show that the accelerator on the FPGA layer can reduce the power and an ADP at the function level and the application level. And thanks teacher for listening to my presentation for this scientific paper.